get to that, probably not about this year. Maybe, but I almost felt like she.
Dang it. That's what I forgot.
Oh.
Oh, cool. So last time we stopped, we went over like parts of a binary tree. We have the root. We have leaves. We've got internodes. Is a binary tree equal to a binary search tree? No, so a binary tree is just structure. You have a node with at most 2 children, and the contents doesn't matter. Whereas in a binary search tree, order matters. Everything on this side is smaller than everything on that side. What's the height of a tree?
How many levels down?
So longest path from the root to the furthest leaf. You can count levels 1, 2, 3, 4, 5, and say that's the height, or 1, 2, 3, 4. How many edges? I'll take both typically, especially if you say what you're doing, because it's different depending on where you read. How do you know if a tree is balanced?
Yeah, more than one level. And I'm struggling to figure out the words how to say.
You said it right.
Can't have more than one really long side and one really short side.
A difference by no more than 1 from each subtree. So obviously balanced, full, and complete. Is it full? No, but it's
No, but
complete.
it's complete and balanced.
And balanced. Is this complete? No, because complete means you fill it in from left to right. So this is balanced, but it's not full and it's not complete. The reason I'm making that a point is because when we jump over to our array-based implementation, oh, this is where I said we would start today, huh? Have we done this yet? We just loaded up a tree, and then I mentioned this, right? Okay. Let's.
And got the new markers.
I forgot. It was on my phone, and it buzzed me 30 minutes before class, and I went back to grading. And said, I'll remember. And then I stood in my office like this, literally like, we're getting some. And I walked up to class. So let's put in some values like 15. Try this red marker. Maybe you are not. My fault. Can't get mad.
Yeah.
You're late.
Crash.
You crashed?
Oh, yeah. Print and the visual.
Oh, but if you would have printed it last night, it wouldn't be an issue. Okay, my random number generator. Let's load up a binary search tree. So we take the first value, we look at our tree, there's no tree, root is null. So we allocate memory, we put our value into memory. We've got 2 pointers pointing to null, null in our node. And we have a binary search tree with 1 element. In the array implementation, we're going to do a little differently. We're going to ignore the first spot because to calculate left and right child, we'll get there in a second. So the very first spot we put a value is 15. Okay. So remember, so when we start to load a binary search tree, we need to compare situational awareness, people. So next value we look at, we're going to compare to the root of the tree, and we're going to decide to go left or right. So 8 is less than, we need to go left. So we allocate memory, we link these together. Okay. So how do we decide which way is left and which way is right in an array? Well, left is equal to 2 times I, and right is equal to 2 times I plus 1, where I is your index. So when we start off, we're going to say, okay, 1 is the root of our tree every time. So I would be at 1. And then we take our value 8. You're done. We take our value 8 and we compare to the root of the tree. Well, we already know we're going left. So 2 times 1 is 2. There we go. And then we look, is there anybody at 2? No. So 8 goes here. Okay. 16, just to make my life easier. So look at 16. 16 is greater than 15, so we go right. Okay. Now, in our array, index is still 1. And we look, is 16 less than or greater than the element at 1 in the array? 16 is greater than that, so we go right. So 2 times I plus 1. 2 times 1 is 2, plus 1 is 3. So the 16 goes here. Okay. Next, 10. So 10 is less than 15. We go down. 10 is greater than 8. So we go right. So we allocate memory, link it to the right side of 8 as the right child. 10, array based. So index is 1, and so 10 is less than 15. So we go left. So 2 times 1 is 2. Our new index is 2, and we look, oh, there's something there. I can't put you there. So I got to compare to you. 10 is greater than 8. All right, so it's greater than, we go right. So my new index is 2 times 2 plus 1, which is 5. So 10 goes to the 5th location. We good? So this could get ugly. I don't know if you noticed already, but it could get ugly here in a minute. 4, oh, that's a good value. 4 is less than 15, we go left. 4 is less than 8, we go left. And this is null, so we can put our 4 here. So we always start off at the root. 4 is, we go to position 1. 4 is less than 15. Less than, we go left. So index is 2. So 4 is less than 8. We go left. So 2 times 2 is 4. Index is 4. Oh, there's a slot. So the 4 can go there. Which, look at our tree. Is it full? Is it complete? So complete means we fill in from left to right. So if your tree is complete, fitting into an array is nice. Okay, let's keep going. So 7. 7 is less than 15. 7 is less than 8. 7, so we go left. 7 is greater than 4, so we go right. There's a null pointer here, so we allocate memory and we link in the 7. Start off at 1. 7 is less than 15. We go left. 2 times 1 is 2. 7 is less than 8, so we go left. So 2 times 2 is 4. 7 is less or greater than 4, so we go right. So 2 times 4 is 8, plus 1 is 9. Ooh, shit. Right? Not complete. So there's 1, 2, 3 things that could fit in there. 1, 2, 3. Guess all we good. Okay, 13. Less than 15. Oh, we're abusing the left tree, the left subtree. 13 is less than 15, so we go left. 13 is greater than 8, so we go right. 13 is greater than 10, so we go right. Okay. While we're looking at this, remember all the values on the left-hand side are less than 15. Accurate. All the values on the right are greater than 15. If we were to look at just 8, and it's its own tree, all the values left of 8 are less than 8. True. All the values to the right-hand side are greater than 8. True. Look at 4 as its own subtree. Anything left, well, there's nothing, and then everything to the right-hand side, it's greater than 4. So like that whole recursive solution, every subtree is its own tree. All the values on the left-hand side are less than, all the values on the right-hand side are greater than. Okay, let's add our 13 here. So start off at 1. 13 is less than 15, so we go left. We get a 2. 13 is greater than 8, so we go right. So we go 2 times 2 is 4 plus 1, we get a 5. 13 is greater than 10, so we go right. So 2 times 5 is 10 plus 1 is 11. We look at 11, oh, it's empty, so we can put a 13 here. Where's the 1 gonna go? Over here. There's a nice little spot for it right there, right? Less than, null. So we get a 1. Since it went right here, are we gonna go off the end of this array? Or will it fit nicely in there? It's 4's left child, right? So 4's left child is 2 times 4 is 8. So the 1 would go here. And then, let's see, what would a bad value be? Well, anything 14. So if we add 14, forget 17 for now, 17 would go here. So 17 would be 16's right-hand child. 16's right-hand child is 2 times 3 plus 1, 7. So 17 would go there. But if I put in the value 14, 14's less than, 14's greater than, 14's greater than, 14's greater than. Shit. So 14 is the right-hand child of 13. 2 times 11 plus 1 is 23. So for sparse, like non-balanced, non-complete binary trees, arrays suck at storing. However, if you have control over the data going in, we can, and you know it's going to be somewhere, something close to a complete tree, okay, then they're not so bad. So, but you don't, that's not something you want to do if you don't have a clue. Because now you could have, what if I entered values in order, like 2, 4, 6, 8, 10, 12. That array would be huge compared to the amount of data you're putting in it, right? Because we're just going right, and then we're jumping further It's like this quadratic pattern. Boom, boom, boom. So, but that's okay. Because the data structure we're going to talk about today, it's called the binary heap. And the reason why I bring up trees and give you the parts and the pieces, and we learn about the relationship between a binary tree and an array, is because a binary heap is a data structure that has a partial ordering, but it fits into an array nicely because a binary heap is always a complete tree. So what is a heap? Can I erase this stuff? It's on video. I'll keep my array. That's a lot of memory I had to allocate. Oh, I should have did that.
Too late.
Too late. Undo, where's Control Z? So a binary heap is a partially ordered set of values that always has either the minimum or the maximum value at the top of the tree. Okay, what is that good for? Have I mentioned priority queues yet? I could spell.
That's what spell check is for.
It really does dumb us down. I spell there, THIER, every time, and it just corrects it, and I even know I'm doing it, and I don't, it just, whoop. And I'm like, I know it's EIR, but my hands type IE. Okay. So remember, array-based structures, list-based structures. If you can store a structure in an array, that's kind of where you want to go because it's so efficient, easy to access. And that's where binary heaps fit. So what's a binary heap? It's a type of priority queue. What's a priority queue? A priority queue is a type of structure that orders things based on a priority, like a number. Like if you have a print queue, it doesn't happen nowadays, but maybe internet? Yeah, let's say some Google CEO is traversing the net, like looking for things. No, is that a good example either? Trying to figure out a way to prioritize packets on a TCP/IP network.
About cell phone tower, like, everyone's first in, first out until EMS. hijacks it.
So their packets have a priority message, which puts them to the front of the queue. And so there's the first packets to get sent on their way to down the network. It used to be the same for video streaming services. Video packets had a higher priority because when you're streaming, you don't want your video buffering, you know? So if there was a lot of traffic, stuff that could wait, like SMS messages or just like email messages on a network, you know, they could get pushed to the back because they're not high priority. But at video streaming, their priority goes up, they go to the front of the queue, and then they get sent down the network before all these other slow text that doesn't really matter. So that's where priority queues are used in a lot of places. Where else might we find a priority queue? Anything even in real life?
Theme parks.
Fast pass bastards. So they have a higher priority when they're at Six Flags and they jump the line and you just want to. Yeah. Well, it's not even fast pass.
Something with airport boarding.
Yeah. If you've already been cleared through the TSA, you got a higher priority. I don't know. There's lots of things you do in computers. Like even if like you're in the lab and everybody prints at the same time. We don't have it implemented, but we could implement it so certain people had a higher priority so that their print job would go to the front of the print queue. So if a bunch of students were printing stuff and faculty came in, it would go in front of all the students. So anyway, that's how we implement things that have priority, is we use something like a binary heap. I think we did in here, I did a linked list, we did an ordered insert, right, with names. Like we're ordering based on an alphabetized names If I just change that to a priority value like an integer and put people with a higher priority to the front of that linked list, that's the same thing as a priority queue. However, a priority queue implemented with a linked list has big O of N performance. Whereas a binary heap has big O of log n. And it also has big O of 1 removal because the item at the front you can remove in constant time. But then the cost to kind of shuffle it around is big O of log n. So yeah, it has good performance and it fits real well in an array. Well, how do we implement that? So if I were to create an ordered linked list with these values like 3, 9, let's say lower numbers go to the front. 2, 5, 7, 1. So if I have a linked list and I allocate memory, I put my data in the node, my next, here's my head. Next is null, 9 comes in, we look, 9 is greater than, so it goes there, we got null. 2 comes in, so remember we had different kind of certs, but let's say we weren't being fancy and we had to stick the 2 here, then we would have to bubble this 2 up to the front, right? We'd have to swap 9 and 2, swap 2 and 3, and so we end up with 2, 3, 9. What was that cost of making that 2 go up to the front? N, right? Because we had n items, so I had to go n times. So if I keep adding, I add a 5. Well, 5 and 9, 5 is less than 9, so higher priority, so we swap the 5 and the 9. 7. 7 is less than 9, so we swap the 7 and the 9. And then finally, we put in a 1. Shit. So there's your order n. Swap, 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 swap. Oh, I'd have to swap 7 and 9. Whatever. But you guys get the point is, putting it in a linked list, we end up with this order n performance, and then worst case is I put it at the end of the list, and I have to go swap with everybody to get it to the front. With a binary heap, since we're storing it so that it looks like a binary tree, what's the height of a balanced binary tree? Log n. So if I stick a value at the bottom of the tree and it has to bubble all the way to the top, at worst, you're looking at log n number of items. Log n beats order n every time. Okay, so let's use these same values, but we'll stick them into a binary heap. So there's a couple of rules with a binary heap. If we're going to do a min heap, then that's what we'll do. Min heap. A min heap just means the minimum value in the heap will be at the top every time, all the time. Okay, that's what you're guaranteed. And then the rules are, just swap the rules for a max heap. The rules are, if I'm smaller than my parent, I swap with my parent. That's it. There's no rules about left side being all less than, right side being all greater than. It's just if I get inserted into a binary heap, and if I'm less than my parent, I swap with my parent. And then you keep looking to see if you keep going. So in a binary heap, we have an empty tree, we put a 3 in. We have 9. So in a binary, and we'll do the array in a second. Man. When we insert into a binary heap, if we had this list-based structure, we would find the leftmost open spot, and we would stick our value in. And then I check, am I smaller than my parent? No. We insert into a binary heap. We find the next open spot, 2. And am I smaller than my parent? Yeah. So we have to bubble this value up. So 2, 3. This is like a binary search tree. No, 9 greater than 2, and it's on the left. But that's okay, because the rules are basically in this binary heap, the smallest value out of all of them is at the top, and the both children are greater than its parent. So we stick a 5 in, find the next open spot as if it were a complete tree. And then we start checking. Am I smaller than my parent? Yep. So we swap the 5 and the 9. And then we get the 7. We find the next available spot as if it were a complete tree. And we put it in. Let me check. Am I smaller than my parent? No. Do we need to do anything? No. Then I insert the 1. Find the next available spot. So finding the next available spot, if we were using a list-based implementation, not that easy. But when we use the array-based implementation, you'll see how easy it is. So 1's less than 3, so we swap. I need some quality control on my nodes, they're not the same size. 1 is less than 2, so we swap. And there we go. So when you look at a binary heap, the order is not apparent. You just know that the smallest value in a min heap is at the top. And then every parent is less than their children. Like comparing children, being you be greater, you be less, it doesn't matter. Okay. So that's building a heap or loading a heap one by one. There's also another method called build heap. We'll do that in a little later. Let's do the array version, and you'll see why it kind of fits. So in the array version, we insert a 3. You find the next available spot. Like I is 1 is the top, so we put a 3 in. By the way, we were bubbling up here, right? I would stick at the bottom. And so I was comparing myself to my parent. How do I know who my parent is? Do I need DNA? That is very insensitive, whoever said that. They didn't want you anyway, that's why they dropped you at the fire station. That's my story. Who's my parent? Well, if I know left child is 2 times I, 2 times I plus 1 is my right child, then it's just I div 2 is my parent. Oh, that's integer, but we're in C++, so it's just this. So divide my index by 2, that's my parent. So the 3 gets inserted, we insert the 9. The back of the heap, let's call this back of the heap. What language was that? So there's always like an index at the back. So we insert the 9 at the rear. And then, so now I look, am I less than my parent? Well, who's my parent? 2 div 2 is 1. I am not less than my parent. So then, nowhere else to go. So insert the next value. Well, the back of the heap is 3. So we insert 2 at the rear. And I say, okay, now I got to figure out where I go. Well, I need to compare myself to my parent. So I'm at position 3. Who's my parent? 3 divided by 3 div 2, 1.5 or 1. So it's 2 less than its parent? Oh, it is. So we do a swap. And then I keep going. Who's my parent? 1 div 2 is, well, 0. So that would terminate whatever that was happening. Okay. So then we insert a 5. Where? At the back of the heap. See how this fits in an array now? There's no big calculating a left child who's way far away. Just filling them into the next spot that's open. And we make sure all the values are in a nice complete tree. So there's no big gaps, it just works. So I need to compare myself to my parent. Well, who's my parent? 4 div 2 is 2. 5 is less than 9, so we swap. So, compare myself to my parent. 2 div 2 is 1, 5 is not less than that, and then 1 div 2 is 0, we would stop. So then we insert the 7 at the back. And so I compare myself to my parent. 5 div 2 is 2, 7 is not less than 5. So we just stop. I know this is getting boring. So we insert last one at the back, 6. So 6 div 2, my parent is 3. 1 is less than 3, so we swap. And then we look. 1 is less than 2, so we swap. Because 3 div 2 is position 1. 2, 1, and we would stop. So let me ask you this. When I bubble up a value, do I have to worry about any other part of the tree? Like, do I have to like move stuff around to make sure it's still a heap? No. I mean, you think maybe because you're altering things, that things like when you change things around. But if you look at the way it works, so let's say, let me just make a new one. Like 10, 20, 30. This is super contrived. That's my word of this last 2 semesters. Min heap. Smallest value in all of them. Complete tree. Parent smaller than its children. Let me add a couple more. Could I do this? Ooh. Is that still a min heap? The only rule is the parent smaller than its children. You start looking at this 10, 20, the ordering starts getting you. Doesn't matter. Is this smallest value in all of these values? Yes. Is this value smaller than its 2 children? Yes. This value smaller than its children? Yes. Okay. So if I insert another value into my heap, let's say I insert like a 15. Okay. So if I insert a 15, and then I got to compare it to my parent. Well, it's smaller, so we swap. So 40 is down here, 15 is here. 15 is less than 40, so it fills the rule. The parent is smaller than its children. But now, we have to make a decision to swap. So if I would write a little better example, this number would maybe be smaller, but my point is, if this value is smaller than this value, some people might think, well, we might have to swap the other child. Well, you couldn't. You would never have to swap the other child because they would have already swapped because it would have already been smaller because in the previous state, they would have already handled it. So the fact that we're bubbling one value up by swapping it with its parent, you never have to worry about the other child because if they were smaller, they would have already been swapped. And that's the value that you'd be compared to. So it's maintaining state, from instance to instance, just fine. Okay. So it's weird to look at an array when we'll probably write some code and print it out, but it's going to be weird to look at it because just by looking at it, you can't tell if it's a heap or not. You really have to do the parent thing. This is what makes it look, you can tell because visually it's what we're supposed to picture. Okay. There's other methods that are involved with a binary heap. You've got like remove method. If it's a binary heap, usually it's like remove min, or if it's a min heap, they say remove min. But if you make it generic, so you can make it a min or a max, just get rid of the min. Say like, there's obviously a push method. Then there's some private methods like bubble up. Because when you add a method, when you add an item, you push it on. Where do you push it? At the very end. And then you have to call an internal method that says bubble up. Go put this in the proper place. And we'll implement all of these. There's also another one called heapify. And what heapify is, you give it an entire array of items out of order, and it'll put it into heap order. And that's where you can really save time and get a better performance. So you can sort, that's why there's a sorting algorithm called heap sort that runs in big O of n log n. You get n items and they get sorted in log n time. And it's even faster if you use a little tiny faster when you use heapify. Let's go over that real quick before we do some coding. Let's just say I have some random, we're doing them in heap. That is not in any kind of order. But if I wanted to run heapify on that, I wanted to take this and turn it into a heap. What's your guess on the cost of that? So we say n. It's better than n. Huh? Yeah, it's because, and here's the kicker. Remember earlier I said left is equal to 2 times I, and then right is equal to 2 times I plus 1, and then parent is equal to I div 2. So when you start bubbling things up, once you get halfway done with the array of bubbling things up, you're done. Because look, get rid of, just to make it look better. How many items are in the bottom here in the leaves? 4. So the leaves are always more than the inner nodes in the root. So once you start like looking at the bottom and then bubbling, getting 4 into the right place and then getting the other into the right place, you're only working on half the array. Does that make any sense? Because by the time you get up here, all the comparisons are going to fail because you're done. Because you've just swapped all the leaves with the inner nodes. So anybody that was smaller is going to be smaller. That's a pretty oversimplification, but that's basically why heapify is a lot faster than inserting an item one at a time. That's what we get better than n log n. Let's write some code. The question is, can we write a heap in, when do we get out of here? 150? We got time. Challenge accepted. Sit down for this. Probably shouldn't sit down. That's why I'm fat. I've been sitting at home. It's horrible. At least I have motivation to diet now because I'm in public. At home, when you bend over, just tie your shoes and your stomach stops you. You don't know, nobody can see but you. It's horrible. It's embarrassing. Especially when you're used to being in shape and playing sports. Don't get old, people, man. It sucks. That's why Griffin's so angry all the time. All right. Heap. We'll call it min heap. Okay. So we know that, and I'm not going to do this the whole semester. We'll get to the point where we got to do PowerPoints with like bigger, tougher data structures.
But I like coding, and students always like it too. Not when I'm struggling coding, but. So how are we know we want to use an array, right? So we'll use integers, pointer, and we'll just call it array. Private. Stupid saran wrap up here. Everybody's all germaphobe. COVID. I've had COVID. It's stupid. My parents had COVID. They were both 80. I was terrified, but they did good too. No, it is a thing. Sorry, I'm downplaying it. And now I'm rambling and I forgot where I was. So we need a constructor, min-heap. Okay. So if we're going to have a heap, based on what we've been talking about, what other data elements might we need, data members in our class, things we need to keep track of?
Size variable.
Huh?
Size variable.
We could use a size variable. Okay, all variables would be lowercase. Okay, array, why is that a keyword? That's not a keyword. We're just going to call this H. Okay. We also need back, right? To know where the back of the array is, the end of the array. So know where to insert it. We're also going to, let's make some private methods to calculate left. We don't have to do this. It's just simple arithmetic, but it reads better when you write it out. So left is, we're going to get an index I, and we're just going to return 2 times I. And then right, we're going to return 2 times I plus 1. Do I need to parenthesize anything? No, because order operations there is just fine. And then might as well add parent. And then we just return I div 2. Okay. So we'll use those as private members. That'll be helpful. We got a constructor. And so we're going to say H is equal to a new int of some whatever size. We'll do a, I don't know, sound good? Let's make it 100. So we don't have to do much error checking at first. We need to set back is equal to 1, right? Because we don't use the 0th index. Nobody asked me why I put an X in 0. Maybe y'all figured it out because you're smarter than me, but why don't we use the 0th index? Huh? Yeah, so yeah, it just messes it up. 2 times 0 times anything is 0. So yeah, so you can't use that very first position with index 0. So we set up back to 1, size in this one is 100. Okay. So we need a push method, void push. Okay, what does our push method do? Over there, we just looked at the very back of the array and we just stuck it on there, right? Okay. So push, obviously we need to push some kind of an item, int I or X. And then, so we would say H sub back is equal to X. And then we would increment back plus plus. No error checking yet. Sound legit? We got this going on? Okay. You guys sure? I haven't done any left child, right child. Do I? So mostly right now, it's just looking at your parent and deciding if you're going to swap with them. So after we push a value onto the back of the array, giving us our complete tree, we need to call bubble up. with the previous location. So we'll say back -1. Okay, it's like, I don't know what you're talking about, guy. So let's write bubble up. Void bubble up, integer I, it's an index. Okay, so we know that we're going to look at our parent and by continuously dividing I by 2 until we can move no further. So I'm going to have a while loop while I is greater than or something to 1 maybe. And we'll say we get a variable for parent. Okay, what now? I'm doing all the work here. This is kind of bullshit. Okay, I just made a generic skeleton class, right? It's got some private methods, left, right, parent.
At that point, you do a statement.
A what?
If statement.
An if statement.
Yeah.
Okay, so we get a parent and then we say what? If
if H sub I is greater than H sub parent.
let's make parent P. You guys agree with that?
Yeah.
Okay. God dang it. The saran, okay, I'll stand. The saran wrap is hard to see through nowadays. No, I'm not having a stroke. I'm okay. Sometimes it feels like it though. All right, so if H sub I is greater than my parent, but I'm in a min heap, so I want to know if I'm less than. Okay, then I do something. So we swap them, right? So let's write a swap. There's a lot of private methods going on here. This should be an OOP class. So void swap integer I, comma, integer j. And so a traditional swap, if you get 2 values, you can say like integer temp is equal to H sub I. H sub I is equal to H sub j. And then H. Okay, so since this array is local, we don't have to return anything. We don't have to do anything. It just, that swap just happened. And so, and let's put, well, alphabetically, we can keep it there. So we would say swap I and P, right? Okay, so shall we go over the logic and see if it matches up with what we think? So we can start off with a fictitious so we know this is a heap, right? So we could say 10, 15, 30, and then 15's left child is 20. So 20 goes there. 15's right child is 50. 50. 30's left child, which is 6, is 45. And its right child is 47. Okay. That's a heap, mini. And so if we were to add, we don't want to, yeah, let's make it go all the way to the top, 5. So we add a 5. We put a 5 in here. and back is now here. And then we call bubble up with back minus 1, which was 8, right? So in bubble up, I is 8. And then we set P equal to 0 initially. And then we say, well, I is greater than or equal to 1. It is. P is equal to parent of I. Parent of I is 4. If H sub I, if our heat sub I is 8, is less than H sub 4, then we run the swap. Okay, so we're swapping 5 and 20. And then, missing something. We do, but I is still 8. We need to, I is now what? I is equal to the parent. So the whole inside this, now we can say if we do a swap, then I is equal to P. And we say I is now 4. But then we hit the bottom, we'll come back up. Is I greater than 1? Yeah. P is equal to parent. Okay, good. So it's 2. Then I look. Is 5 less than 15? Yeah. So we swap 5 and 15. And then I is equal to P. I gets 2. We go up. Is I greater than or equal to 1? Yes. P is equal to parent. 1. Is H sub I less than P sub I? Yep. So we swap 5 and 10.
You're gonna need to take out that equal sign, aren't you?
Huh?
Well, you need to take out that equal sign on the while I is greater than or equal to.
Maybe. So we'll say I is equal to P, 1. And yeah. So if it was greater than or equal to 1, we would continue, and we don't need to continue. So it's just greater. Or is it? Yeah, it is. I feel like I'm missing something, but every problem we solve a bunch of different ways. So at this point, hopefully, we've got a push. We've got a size that we don't use. So let's go in push. We're going to say size plus plus. So we maintain how many items we got in there, just so we can print it out. Now I'm going to add a print method so we can get out of here in a second. Well, maybe not. I got time. Void print. Should we overload OStream, OOP people? I'm kidding. Print. And so we're going to say for integer I is equal to 0, I is less than size, I plus plus, C out, H sub I, space, and then C out. Okay. If this works, I better get some applause. So we got, what's it called? We have got a min heap. Okay, so we're making our own data type, min heap. So min heap, I didn't mean to do that. H, default constructor of size 100. And then we'll say well, let's add some values so we know what the shape should be. So H dot, is it push? Push. I don't know what was going on right there. So if we push those values that are in that tree right there, we should get something that we could debug on the screen when we print it out. So 10, well, no, we want swapping. So just Can you read them to me in reverse order, like 47, 45?
45, 50, 20, 30, 15, and 10.
Okay. And then we need to print it. All right. It's not stopping. So usually when it's not stopping, it's in the loop somewhere. Dang it. So what do we do? Let's make sure we're thinking right. When we push, back is always pointing at the back item, right? So we say H sub back gets X, which is what we pass in. We increment back, we increment size. We call bubble up with back -1 to bring us back to pointing at that last item. Let's see out size just to see what's going on. If it gets stuck or if it just keeps going. Okay, so it got stuck on inserting the 4th value. That's, no. It looped 101 times the first time, 102 times the second time.
In your default constructor, your min heap one, you got size set to 100, and then you're incrementing it in the push.
Oh. Okay, I was using size not like it should be. So we need size. So we need, let's change this around. I'm going to call this current size, and we also, let's say, integer heap size. So then in our constructor, good catch, thank you. So in our constructor, we're going to say heap size is equal to 100, and then current size is equal to 0. And then here we'll, every time we add an item, we'll say current size. Okay. And then while it's less than current size, semicolon. Let's try again. So I print out 1, 2, 3 and got stuck. So on the third item, so let's look, this is fun. Let's do this. It's obviously, okay, so 0 and 45, that doesn't look right at all, right? So first of all, part of that problem is me, because when you print, we start at 1, and then we say less than current size. It should be less than or equal to current size, since we're doing 1 indexing. Okay, we're good there. But that's just the print. But that's important because we want it to reflect what's actually what we think is in the array. All right, so let's add another one. So if we have 47 and 50, 47 would be at the very smallest place in the array, and then 45 gets entered, and it should swap, right? And it does. But then when we add 50, it should not swap. So let's look. We call bubble up no matter what, right? Is that okay? It should be okay. So we go to bubble up, and it's not okay because there is no test to see if I even need to be bubbled up. So I think that's where we run into our first problem is 50 is not bigger or not smaller than its parent. And we're still trying to loop while I is greater than 1, and it never does anything. P and I will never change because this will never evaluate to true. So we have to, part of our loop, we have to know when to quit. And we also don't want to waste time. Like when I add an element to the end, and I want to say if H sub I is less than H sub P, I call swap. Else return. Is that too much? Is that too heavy-handed? because you only want to swap when it's less than. If it's not less than, you kind of want to be done, right? So these are the discussions that if you should really be listening, because this is the stuff that makes us understand it. I know, I mean, I get silly and all that, but seriously, this is an important part. So we know that when we add an element to a heap, that we need to put it in its correct location. And part of algorithms is being unambiguous and correct. So we were not correct, and we were kind of ambiguous with our logic, right? So hopefully, when I say, is this too heavy-handed, am I killing this method too fast? If one of these fails, should I end looping? And I think we do.
Yeah, at that point, because at that point it should be.
Yeah, even if you get entered at the end and you're the largest value and you don't want to do anything. So you'll come up here once, you'll set up some variables, you'll start a loop. You will not be less than your parent. And so you'll just return because we're not going anywhere. So I'm hoping. All right. So now we did it for the one, we did it for the couple, now we do it for the many, just like in problem solving. And doesn't it feel good? I like it every time. I've been doing it forever. Is that the right order?
Well, I read it from the heap drawing, not the every one.
So 10 is the root, and then it's left and right child are 30 and 15. And then 30's left child and right child are 47 and 50. And then 15's left and right, 50 and 20. So it doesn't look like there's any order, but it's in heap order. And then so if we add what did we add that last time? We added one more that bubbled up, 5. So let's print it before the 5. And then let's print it after the 5. Whatever. Guys think you're so awesome. Come on, that's cool, man. This is good. Okay.
Is there an easy way to grab like a tree?
No, there's not an easy way, but there is a way. You have to calculate how big it is first, and then you do that many spaces out to center the root on the screen. Yeah, it gets ugly. I've tried many times, and it's always ugly. But there's other ways to like push it off to the left, and then everything kind of grows down. But still, not today, not in here. There is this thing called GraphViz we will use. So GraphViz, shit. Google got me. I've been using DuckDuckGo because I'm boycotting Google right now for my searches.
You're still using Google Chrome.
Yeah, I know. I can't not use Google Chrome because of developer tools. I'm still a developer. If you got a better alternative, I've tried Firefox and that. So GraphViz visualizes data structures. And then there's actually an online GraphViz that I have a class I wrote. I'll find the GraphViz stuff. And you can just cut and paste. Like I'll have a class that will go through like a data structure and print out the right syntax. And then you can paste it into GraphViz and it'll create an image of what your data structure looks like. So Byron, you're on the right track because we'll do some of that too. All right, so here's one cool thing though. And I don't think we'll finish this, but now I have to be able to remove an item. And we won't finish today, but we'll finish next lecture. So when I remove an item, we'll call it extract because that's what the books call it, extract min, extract max. So all extract does is say, well, we're going to return an int. And then so when we extract an item from our heap, we're going to say integer temp is equal to h sub 1. Okay. So when we remove an item from our heap, get a copy of it, so like the 5. So temp is 5. Okay. So now, oh shit, did we just shift up? Doesn't work that. So the cool thing about storing it in an array and about keeping it like complete in a nice structure like this, we can take this element here, that value, we overwrite what was there, 20, and then we would have another private method called bubble down instead of bubble up. So then we say, all right, we just reverse our logic and we start going down. Am I greater than my children? You know, and so we swap the other way. But still, the cost on this at most is log n because the tree is whoop. So removing an item is a cost of 1 constant time, and a cost of getting that, doing the swap is constant time, but then getting it into its proper location is a cost of log n. So that's why if we run like a bunch of pushes, which is n, and then log n to put them in their proper spot. And then we remove all the items. We basically get almost an n log n sorting algorithm because when you remove the minimum value every time, you've just sorted your set of items that you put into the heap. So that's why heaps are so kind of popular and pretty cool. So how, if I extract, now I get temp, I get it to the first value. I need to say back minus minus. We agree? Then I can say h sub 1 is equal to, am I right? Is back always pointing at the last element? Or is it pointing to the, so let's look at our insert. And these are the things when you write your own algorithms, you write your own code, it doesn't matter how you do it, whether you like insert then increment or increment then insert, as long as you're consistent and unambiguous. So when we call push, the back is pointing at the last empty element. So then in our extract, that's why I said, all right, we'll decrement back because that will bring us back to where the last element really is. H sub 1 gets H sub back. And now the next time we insert an item, it'll overwrite that last element that was there. So when I say we swap them, like I brought 20 up, normally when you do it pictorially up there, you swap the 2 values and the 5 gets over, but anyway. And then I need to say bubble down with 1. Now, bubble down, I pass in a 1 because sometimes we might call bubble down from another part of the heap. So you want to pass in the index of where you want to start from. And in this case, when you extract, we want to start at the top of the heap. So then we got 9 minutes. Come on, we got to do this. Now I feel like we should do it. We got to get it done. Just do it. Just do it. Just do it. What do I need to do?
Well, wouldn't it be a case of just going to null up, copy it out, and then switch to the sign?
Kinda. But do you see how this algorithm is, it can be efficient and powerful, but there's code costs, right? There's no more of this simple push and pop, you know, add, remove. It's like, okay, we got these ulterior private methods that make things go where they're supposed to go. So if we're doing a bubble down, we pass in an I, and we can say, well, I is less than back, okay? And we can say, now this is where we're not gonna finish today because when you bubble down, there's a little bit of choosing going on. So let's say I insert or I remove 10, right? So 10 gets removed, the value 47 gets replaced with and then I say bubble down. So earlier, we just compared with our parent, like, index div 2, told me who my parent was. And if I'm smaller than my parent, I continue on. In this case, though, if I bubble down, I've got a choice to make. Because I can't just go left. I got to pick the smaller of the two children to swap with. Otherwise, I'm leaving my heap out of order. So I got to look at my children and go, who's smaller? Well, 15 smaller than 30. So I choose the left child to swap with. So 15, 47. And then I say, all right, basically, are any of my children smaller than me? And then if both of them are smaller, you got to make a choice. Obviously here, only one is smaller. So that's our choice. We swap 47 with 20. And so then we look, we're in heap order, right? Smallest value in the entire heap. Parent looks smaller than children, parent smaller than children. And I'll stop there. I won't kill you guys. I have to tell you guys what.
Instead of doing an else return on the bubble down, bubble up, would it be better to actually do a bool and do the while based on the bool? Like do a bool swap and have that set
Yeah, while it's swapping,
yeah.
keep swapping, else just return. Yeah, I like it. We might change it or change it, grab it and take it at home and change it. No, I like it. Because that reads well. Like while you're swapping, keep looping. Otherwise, it's quit and return. No, I like it a lot. It's cleaner. But we'd have to make swap a bool. Yeah.
Yeah. Well, you sit there and make a bool called swap or whatever.
Well,
It would.
no,
When you say that out
well-
loud, it kind of. Thank you. I do.
we could put a little more logic in the swap
Yeah.
and make it a Boolean. Let me think about it. But I like it. It's clean. Today, Thursday? Awesome. I don't teach tomorrow.